Hello everyone, I'm Shawn, CTO of MultiVAC. So glad to meet you in video. MultiVAC is an all-dimensional sharded protocol. We have been focused on carrying on forward our project. In May 2018, we released our technical white paper, and in September, we released the yellow paper to show many technical details of the sharding solution. In October, we published the MultiVAC lab data. Today, I'm going to show you how our testnet works in this video. Okay, now let's get started. First, let's begin with our all-dimensional sharded scalability solution. Our sharding approach differs from and improves on almost all other existing sharding methods. Scalability is the major bottleneck preventing blockchains from reaching industrial capacity. Systems tackling the most promising scaling solutions thus far, blockchain sharding, have produced progress in parallelizing transaction processing but have not achieved full sharding needed for total scalability. MultiVAC was completely designed to serve as a solution, the world's first fast, efficient, and all-dimensional sharded blockchain designed for total scalability. Transaction sharding alone is not sufficient to solve blockchain's scalability problem. We are the first blockchain system to provide sharding not only for computation, but also for data storage and transmission. In the lab data we released in October, our peak TPS reaches higher than 30,000 on 64 shards with an average of 481 TPS and a maximum of 533 TPS per shard. At the same time, the testnet proves linearly scalability and is able to meet the needs of large-scale decentralized applications. So that's a brief introduction. Now let's come to the next part, MultiVAC Testnet. Now I am going to show the startup process of the MultiVAC Testnet. The picture that everyone sees now is the dashboard of Alibaba Cloud, which is called as Aliyun. This is a data center in Silicon Valley. In this dashboard, we can see the MultiVAC relay server, this server, okay, through which we can upload all our data. The binary of the miner node is transferred to this cloud server and then distributed to all of our miners. So we are now logged in to this server. We can go to the MultiVAC working directory first, where we can see the MultiVAC project files, including all the code. The directory where you can enter is the remote test. In here we can start our main script. Python, then testnet.py. This is our main script to start the whole network. Through this script, we can start some servers, like 40 servers for this test. When we conducted lab tests in October, we used Alibaba Cloud, Amazon AWS, and Microsoft Azure cloud servers. So we can find that some old scripts left. In October, we launched a total of 12,800 nodes. The servers are distributed in data centers such as Sydney, Silicon Valley, London, Virginia, Beijing, Singapore, and so on, so to ensure decentralization of the testnet environment. However, it is very, very expensive to launch such large number of computers. So now we only start 40 nodes for the demonstration, and we will install 4 miners on each computer. So we have 160 miners. And they are distributed into 16 shards. So we have 10 miners in each shard. According to the lab data, it is possible to achieve a TPS close to that of 8 core with 4 times of dual core computers. Thus, the overall performance of the system will not be reduced by computer configuration. We can see that 3,200 dual-core computers can achieve almost the same peak TPS with 800 8-core computers. This feature of MultiVAC can effectively reduce the barriers for miners, which means that each of us can use our ordinary PCs to participate in mining, and in turn the system becomes more decentralized, safer, and more stable. Okay, we can refresh the Aliyun dashboard. Yes, we can see that all the server configuration created are dual core with 4 GB of memory, and it says that the hardware requirements is very low for MultiVAC miner. Okay, now 40 servers have been successfully launched. Now we can start the MultiVAC test network with this command test. Okay, and with this command, we can send all the instructions to 40 machines and also upload the programs of all our miners to all machines. Since the startup process of the entire test network takes a certain amount of time, let us wait patiently. Maybe let me reintroduce the technical features of the MultiVAC sharding solution. Okay, let's go to the slides. The picture we show the data flow of the MultiVAC sharding solution. Each shard of MultiVAC is composed of nodes. Blocks only get transmitted within only one shard, and block headers are transmitted across different shards, so the transmission volume is very small. The interaction between miners and the storage node is a light-weighted data structure called Merkle proof. In our solution, both Merkle proof and block headers are relatively small, and they are enough for the miners to verify the validity of the transactions. The ordinary miner node only needs to save the headers without the whole ledger, and the storage node will keep all blocks for one shard. And for each miner and storage node, the size of transmitted data is proportional to the transactions in only one shard. Okay, let's get back to the testnet. Now you can see the MultiVAC testnet has started. Since this is a demo network, I will not set the TPS very high. The average TPS of each shard is just over 200. Throughout the process, we use Prometheus to monitor all data. Let me check. Okay, Prometheus is working. We use Prometheus to monitor all data, including memory states, disk state, memory, the bandwidth, the CPU load, and so on. So besides the pending transaction, the broadcast rate, the shard max height, the shard size, the TPS, those are monitored by Prometheus, so we can check them. Okay, here we can see 6 pictures of our Grafana's dashboard. We used Grafana's dashboard to relatively completely monitor the whole system, and this is the TPS of each shard, and here this is the broadcast message rate, and this is the shard height. We can find that each shard is proposing their own block, so they have different heights of blocks. And this is the pending transaction. It depends on the loaders that we pushed into each shard. And this is the CPU usage rate. We can find that the CPU usage is about 70% to 90% for each computer, because we have 4 miners in each computer, so this is very efficient. And we also have the memory. Sorry, I have to minimize this image. Okay, this is the memory used demonstration. We find that each computer has less than 4 GB of memory, and we find that there are still about 3 GB free. So our miner used only less than 1 gigabytes of memory. Now let's take a look at the development of MultiVAC's GitHub code. All current MultiVAC source code is on GitHub, in GitHub's MultiVAC tech directory. We currently have 9 repositories, including main network development, blockchain browser, our official website, and our yellow paper, and so on. So the updates and iterations will all be shown on GitHub. However, since our code is in private, if you are not a member of the MultiVAC Foundation, you will not be able to see them. MultiVAC has finished over about 50,000 lines of code, and our system is developed with the Go language. The code library contains a total of 62 folders and almost 400 files. We have installation guide, development guide, and the test guide. Now, MultiVAC's code base includes open source third-party code such as P2P library and JSON packages, as well as MultiVAC's self-developed code, including the Merkle tree-based storage, the storage nodes. Here we have the shard processing mechanism, and we have the VRFs to reshard. So we also have a net interaction based on the innovative design of new storage structure. So in this way, the interaction data between the two nodes can be reduced to very small data amount. In addition, we also designed a transmission method here and this way. So we do not need to the whole network broadcasting. As a result, it solves the transmission bottleneck faced by the current blockchain fields. So we can show some basic code. Okay, so we have this is our sharding processor, and we also have our VRFs. Okay, it's based on Edwards 25519. This is our VRF implementation, and we also have our very interesting Merkle tree-based storage. Okay, so we support very little data transmission to verify the whole block. So we do not need to store the whole ledger of the system. If you would like to know more about MultiVAC, you can also visit our official website. It's www.mtv.ac. You will find our information like technical white paper, sharding yellow paper, and one pager. The technical details are described in our yellow paper. So you are also welcome to discuss more technical details with me. You are welcome to contact me. At the bottom of the screen is my contact information. Thank you for your watching.